I'd like to introduce Dr. Yongchang Liu from the University of Southampton, who has kindly organized today's session and is chairing. Yongchang, over to you.
Okay, thank you very much for introduction. Today, we are very honored to invite two speakers to give the presentation about the sustainable biological nutrients removal as well as recovery. So our first speaker is Juhani Kostiainen. He has been working in the water and wastewater industry for over 40 years. He has experience of sequential batch reactor technology transfer to other countries. He is currently a member of working group of the European Committee for Standardization, which is all compiling draft proposal for new standards required to meet more stringent future demand for medium-sized wastewater treatment plants. He is a member of the International Water Association in 6 working group, a member of the multiple environmental professionals, and a member of the City of the Tempera Waterworks Board, which oversees advancement and audit of the treatment system. Juhani's present focus is on sustainable biological nutrients removal. He is an expert in SBR technology. Juhani currently heads the process team for Plant Work Systems Limited, which is a high-tech, environmentally principled company providing innovative, sustainable solutions to all sectors of the wastewater treatment industry. So, Juhani, I'll hand over to you. Please, Juhani.
Thank you very much. Good afternoon, ladies and gentlemen. What the speaker said in her speech was not the total truth. My wife is saying that my alter ego is just like Faust, who sold his soul to the devil to see a young lady. But I have not sold my soul to the devil, but to the sequencing batch reactor. The most important part of my work with SBR has been developing a working combination of a process and a plant able to reliably and cost efficiently remove phosphorus from wastewaters to very low levels. The answer to the challenge is now available. In the following minutes, I will introduce you the PWS NUTREM process and plant. The idea to develop BNR popped up when we worked with our pure SBR, and there were increasing demand of P removal and dosing used for that. We did tests, and even the reduction results were satisfying. The side effects were frightening. Dramatically increased surplus sludge production, difficulties in sludge treatment, chemicals, endless price increase, health and safety issues, and finally, how to efficiently control the damaging metal traces in final effluent. Deep penetration to BNR technology turned my head, and finally the decision to go further was easy. And there came up the NUTREM, Advanced Biological Nutrient Removal Technology, and sustainable alternative to chemical dosing. To achieve a biological removal of phosphorus and nitrogen requires 3 treatment zones: anaerobic, anoxic, and aerobic. Historically achieved during different tanks in various processes such as Baden-Foe, modified UCT, A2O, Johannesburg, and many others. The cornerstone for the BNR is to understand what microbial process phases are absolutely necessary to be involved and how to carry them on. Anaerobic, anoxic, and aerobic in various orders are required. A big number of so-called conventional AS processes have been proposed and used. But sad story is that the final great success have not been achieved in practice due to several reasons like complicated treatment range, instability in diurnal circumstances, big footprint, dosing demand to reach low enough beta figures, etc. NUTREM provides these conditions in one reactor. It's totally different. The whole thing with various phases is packed into one and single reactor. The prescription can be easily multiplied regarding the size of the plant to be designed. What is important to notice is that the process phases are separated from each other by time rather than physical space and volume in form of various numbers of tanks. This basic difference provides benefits in great flexibility in process control, small footprint, and a better price. Here you can see the indicative process diagram in general. The details we will do through later in connection with independent equipment. The front end, normally as usual, 6 mm screening and grit removal and FOG in special cases. There's an offline VFA factory to boost the functioning of BTF, which plays a double role as a flow balancer and a holding capacity to allow dump fill into the reactor. The number of BTFs and reactors is determined by the number of loading heads producing the wastewater. The attenuation tank at the rear end is to meet the frequently set max discharge velocities to keep erosion in control in the receiving watercourses. Aerated sludge storage tank is a temporary storage before tankering the sludge treatment centers. In the process, the influent is collected within the balance tank where it is mixed mechanically and gently in set periods to back up the fermentation process. The influent is then fed slowly into the settled sludge blanket within the reactor, whilst the reactor is in settlement mode. The hyperboloid mixer is set to mix a super slow rate and not to break the top of the blanket. The reactor decants the effluent of the preceding cycle by the piston force feeding the effluent out via a special siphon decanter. Once decanting is completed, the transfer completes and the reactor fills. Regarding the targets, the reactor is then either anoxically mixed or aerated. And second, anoxic and aerobic phases can be performed, and the process then repeats. So it's doing the same thing again. From the balance tank to the reactor, then anoxic mixing or aerated mixing and settling and repeating and discharging again. As far as we know, NUTREM BTF. Here's the balance tank fermenter combination. This combination is an offline hydrolyzing booster and inline BTF. It's one of the key parts of the process. It's well known that the P removal process is a reciprocating P release and P luxury uptake partial processes performed by PAOs. To work, The PAO bacteria needs energy, which is introduced in form of VFAs, the volatile fatty acids produced from readily biodegradable COD in the raw sewage. The spiral separator takes 10% of primary sludge at all flow conditions, from the dry weather flow to final treatment or storm conditions. The flow from the spiral separator is fed to the hydrolyzing tank in 3% suspect solids content. Thin sludge, which is after sufficient time diluted by a dilution water from the BTF and then returned back as 1% to the BTF. This triggers a stress factor which is dramatically enhancing the fermentation of raw sewage and the raw sewage is then fed into the reactor. In the BTF, there is also a recirculation pump which discharges back into the tank via a high pressure nozzle, sharing the stuff loose from the outer surface of the particles and convert them to the RBCOD. BTF is working in the interface of acetogenic and acidogenic phases of fermentation, and the content of the BTF is then pumped out into the reactors. As far as we know, no one else has anything comparable to tackle the problems caused by diluted storm flows, which easily can destroy the pea removal capacity in conventional processes. Simplicity and robustness and low price for a good insurance, which is normally not the case with the insurance companies, and it's done here for the pea removal. This is one of the key parts of the NUTREM process. Here's a view from inside the BTF. There is a slowly rotating mixer scraper close to the bottom of the tank, gently mixing frequently the content of the BTF, and that intensifies the fermentation, and on the other hand it moves the thickened settled sludge towards the outlet opening for desludging. Fed into the reactor takes place at the top of the settled sludge blanket, which is one way to keep the settled sludge blanket in standard height. NUTREM reactor seen from inside. You again see the circular tank, mostly made in our case is in glass fused steel tanks or at site cast concrete or slab made. And in the middle of the reactor is the hyperboloid mixer aerator. And on the outer circle you can see the sharing fins which share the air and aeration phase, an air pipe feeding the air into the sparger ring which is underneath the hyperboloid mixer, and baffle plates to prevent the whirlpool effect during the anoxic mixing, when there is only mixing on and not the aeration. When used for aeration, the air is introduced under the mixer body, the sponsor ring, and the sharing fins run the air. Oh, so this is very interesting. As you see, the air is widespread over the whole bottom of the tank with small vertices mixing it with the tank, and there are no dead spots which are found with fine bubble diffusers systems where the diffusers can be far from each other and the bubbles are rising directly upwards and not mix the whole bottom of the tank. This schematic shows the hyperboloid mixer in a NUTREM reactor. The sewage from the BTF is introduced from underneath the hyperboloid mixer, whilst the mixer rotates very slowly. The contact in between the incoming raw sewage and settled working anaerobic sludge is ideal. This is a real winning property of NUTREM. The sewage fully mixed with the settled biomass and infiltrates upwards through the sludge, contacting the worth of gold PaOs, which release the phosphorus in the cell mass to surrounding bulk liquid. We call this a piston effect. The final effluent is then discharged via the siphon decanter, whilst the first phase of the treatment occurs at the bottom of the tank, here, when the raw sewage is meeting the working anaerobic sludge. And the results is here. This is the depth from the bottom of the tank of the sampling points. The blanket is in practice very close to 2 meters in our big tanks, which had a 5.9 meter aeration height. And the red curves shows mixed liquor suspended solids, which at the bottom are almost 8,000 milligrams per liter and gradually decrease when it's rising up, and in 1 meter there is almost nothing left, and in 2 meters where's the blanket top level, the whole settled mass in tightly there, and the blanket top is sharp like a knife, we say, and released phosphorus at the bottom, where it has been the longest time in the contact with the incoming raw sewage. The released phosphorus concentration can be 200 milligrams per liter, and gradually decreasing the higher the measuring point is, and in 2 meters there is no, almost can say no phosphorus in the bulk liquid. This is surprising, and the same now in the table. That sampling height at the bottom, total phosphorus 193, MLSS 8000, and the gradual decrease and gradual increase. The total phosphorus can be 0.15 at the top of the blanket. and suspended solids 5. So which shows the very good settling properties of the active sludge. Why this is important? It is important for the safety margin, because after a full load there is still a 2.5 meter clean water. There is a deliberate stratification in the piston below the discharge point, and this was very hard to believe that the professionals, when we first time introduced the idea of the piston discharge. And in SBR it's important to save time for active phases of the process, and therefore now there is the fill and discharge is combined. The normal water depth is 5.8, 5.9, which provides even larger safety margin, and the 5.8 is there that regarding to calculation, the aeration height 5.9 in an SBR, it gives the best price for capital costs and expenditures. Here's the control system. In the engine room there is a full control system and a screen where the plant manager, plant engineer can look after all things, separator, hydrolyzing tank, how the inflow is coming in, and the flow meters and balance tank fermenter and the level there, which is important. We try to keep the top level as close to the top as possible, and the breathing from the balance tank is avoiding the surface penetration of oxygen by feeding the air out from the BTF into the intake line of the compressors. And then this is a normal case. We would say a normal case in bigger rather than 1,000 population. There are one BTF, the balance tank fermenter, and 2 reactors, which guarantees the limping on if something happens in other one of the reactors, or some services can be done and the plant is still working. And sample chamber and sludge thickener, and then forward out. And here's the balance tank fermenter, and you see the 2 reactors here, and the colored pump shows on what phase is going on, and normal route from the main incoming sewage from via the front end and into the back up BT to the reactors and aerated sludge thickener and sample, and outflow to works, return return. P7 is pumping that out. And where is the home of the pilot plant or test plant, or how do you like to call that? It's at Hants, south of England. It's located at Southwest Water Petersfield sewage treatment plant. That's pretty far from the front end where the flow is coming in, and at the front end there is screening and grit removal, and the main tunnel forward, and there is also the ferric dosing and the intake point for NUTREM is before the dosing to get the real raw sewage there, and the line has been installed here and the test plant is around here. Our normal prescription: balance tank fermenter, reactor 1, reactor 2, aerated sludge storage tank, and this is the main combination. Next one, commissioned September 2014, and there was a limit to take only 50 cubic meters, which was the actual fixed load, and the consistent results demonstrating TP removal down to levels 0.1 and 0.3, and stable operation maintained during winter periods when there was a diluted water. And here are the results: October-March 2014, 2015, and pretty strong influence: 655 COD and 280 BOD, which is the popular ratio 2.2, 2.3, and final effluent respectively BOD, which is under the control there, very low, 330. Ammonia, well, can see that it is diluted, because in the separate sewerage system country this can be 70, 75 or 80 milligrams per liter, but here when all the water is collected into one big sewer, it's diluted. But the result anyway in milligrams per liter, which is the actual result, is 0.28. Total phosphorus also low, but not too low, 683, and out 0.25. And suspended solids very low, also 5.47, which shows the excellent separation in settling period. And the next year we have, as we say, that it's improving the run like a pig on the next turn. So TP is 5.1 and 0.15, which is very good. And this all totally without chemicals. And then we went to the urea test, where the P removal was the #1 target, and then installed the spiral separator and the hydrolyzing booster to improve the VFA production, because the water, the raw sewage, the incoming water was all the time very much diluted, and the fluctuation during the diurnal flow period, it was very big. Sample chamber here, where it's coming, and the siphon decanters can be seen here, and plant return well. And here you can see now how it's arranged. There is the main wastewater treatment flows and the NUTREM plant flows, and the permission to take the water for the urea test was increased to from 50 cubic meters per day to 120 cubic meters per day, to follow the real normal life, how the plant is living. And as you can see, so this is September 30, 3 o'clock at night, 6 in the morning, 9 in the morning, a jump up at noon, and in the evening, as normally, the high point there, and here is now already close to 140 cubic meters. And the NUTREM plant, the form of the curve is similar, totally similar, and the NUTREM is fed regarding to these flows. We have there three strokes per day, or 3 cycles if you like, and 4 various sizes of cycles. And the pillars here, they describe the fill, how much the fill is, and the wider the pillar, the bigger the flow. And you can every day follow these on the screen from home or from office or from the kiosk at site. And here the total phosphorus concentration. Sampling points, and as you see, the influent total phosphorus is changing from less than 1 to 11.5, which would be the dry weather flow case, and then suddenly drop down to close to 2. And the sampling points can see here always. And the total phosphorus concentration curve, close to 0 and 0 and 0 and going on. And then in the reactor 1 happens something which has not been explained ever after that, and the recovery. And if we check the soluble reactive phosphorus, the curves are similar, and same here. And we check that because normally the escaping soluble reactive phosphorus can go very low, and in these cases it went to 0.0 point something, and in the total phosphorus test, which is not filtered, the figure is regarding to the escaping suspended solids, and this was a surprise for us, because if you have soluble reactive phosphorus 1.47 and the suspended solids is 3, and we had two occasions here, 1.47 and 2.8, and the suspended solids 4.5, and in normal samples at the plant, if we had 0.010, the suspended solids could be 5, and another sample 0.011, suspended solids 5.5. So there's no real explanation other than wrong sampling or wrong testing or something, but these results have been anyway included in the report, and without this unhappy thing, the results would be much better, but everything has been honestly put in the records, and that is the final thing. And the influent SRP is following mostly the curve of the reactor 2 and reactor 1. It's for some surprised reason, but the reactor 1 started to load at 8 o'clock in the morning and the reactor 2 at 2 p.m. So the quality of the wastewater is changing very much, fluctuating very much during one day. High quality biological total phosphorus and total nitrogen removal. At Petersfield test and in the Uquia test, which was meant for checking the phosphorus, and it was not concentrated on total nitrogen at all. So what's now happening is that in many parts of the country, the alarms have rung, and the observation of the algae growth is increasing mostly at the Solent area, and the end total nitrogen has popped up to a very important thing, and therefore we had, without any further tricks in the standard P reduction program, we achieved 7 milligrams total phosphorus at Petersfield, but the demand will come down close to 5 or close to 3 even, and therefore we are currently working in conjunction with the University of Southampton to demonstrate simultaneous biological removal of total phosphorus and total nitrogen to very low levels. What are very low levels? In phosphorus it means 0.25, 0.2, 0.1 finally. And it's good to understand that we are chemical-free company, and it's all done without chemicals, and the results achieved until now have been achieved without any tertiary treatment. So this is a very ambitious target. And the total nitrogen in practical levels can be close to 3 milligrams per liter, because total nitrogen contains always such streams which cannot be treated by biological processes. And the other thing is the recovery of P to build up a circular economy principles. P-rich sludge. The PAOs contain a good amount of the phosphorus, and there can be 35 grams per kilo of total dry soil. And it's not chemically bound, so no need for expensive acid treatments, etc. And the acid treatment is not the answer, as I'm following the European phosphorus platform, and in Helsinki followed very closely the acid treatment experiment which finished 2 months back, and the final result was that acid treatment is not the answer. Some cases most of the people propose struvite and several other things, and the price of kilo of phosphorus is 10 times as high as the price of mineable phosphorus. Of course, on the other side there is the threat of the mineable phosphorus finishing. But anyway, the new, something very, very new has to be found to build a circular economy for P recovery. Right. It's here. I thank you very much for your attention, and I'm open for questions, by professional questions. When I first time was in this country at 1990, we had a presentation at St. Peter Hotel at Guernsey Island, very beautiful Victor Hugo ballroom. And after 1 hour's presentation, I said I'm open for questions, and several hands rise up, and the chap in the front row was there, and I said, it's your turn. He popped up and said, who else wants to go to the toilet? So, and other kind of questions, please.
Thank you, Johanni. Thank you very much for your excellent presentation. Yes, there's a lot of interesting questions to you. So I will pick up some questions first, and you probably answer a few questions first. After the Anna's presentation, we can put the question at the end of the session together. Yes. So I think, yeah. So I think, sorry.
It's my pleasure.
Okay. So one question is for the traditional BNR process, if it is well operated, usually the TP can reach as low as 1 milligram per liter. But for NUTREM, you can reach much lower levels, such as 0.1, 0.3 milligram per liter of the TP. What is a critical factor that makes the NUTREM successful to achieve the lower TP?
Which is the availability of VFAs in all phases of the incoming sewage, in diurnal flows especially, because VFA is the key thing, and normally from the readily biodegradable COD cannot be done VFAs enough, and we have the special VFA factory in form of the enzymatic hydrolyzing booster. And it's important to understand that we do not only ferment incoming primary sludge, but we ferment in all circumstances 10% of the incoming primary sludge and in 3% thickness. So it means that it's stable and the VFA production is stable. And the other thing is the ideal contact with the incoming raw sewage and settled anaerobic working sludge. There is no disturbance of the surrounding bulk liquid. The incoming flow with VFAs meet the PAOs under the blanket. There's only the working biomass and the bulk liquid, of course, because it's thin sludge, but the MLSS can be 10,000, or as we saw in the picture, it's 8,000 milligrams per liter. So they are only the working partners and nothing else. And then the excellent selector effect as form of the dump bloat is cultivating the active sludge flocs to a very tight and close particles there, and the settling properties are excellent. So the separation in between the suspended solids and the liquid, it's of top class. And the PAOs who release the phosphorus and luxury uptake the phosphorus, there is more than enough energy to do the job, and the PAOs content in the MLVSS is high. So it means that there are the blue colors enough to do the job.
Okay, thank you very much for your answer. So you mentioned that the sludge settling ability is very good, very high, and there's another question related with another two questions related with this. So did you see the granular sludge formed in your reactor? And what is your sludge SVI?
Well, we are very close to produce the granular sludge. If we would like to discharge early or another way to get the free swimmers who are always escaping there. So as we very well know, the granular sludge is producing all the time escaping suspended solids. So we don't see any reason for granular sludge. It has its advantages, but as now have seen in the practice, it's not a God's gift. It's a process inside other processes and like other processes. And well settling active sludge as what we have, it has proved the ability. So Well, one loves mother and one loves daughter.
Yeah, so this is related with another question. So aerobic granular sludge is based on SBR, so have the similar reactor at the operation with your NUTREM. And do you have the simultaneous filling and decanting? Fill the raw sewage and decant the treated water. So based on what I know, the aerobic granular sludge technology based on Narada also takes the same similar strategy. So why do you use this type of the strategy, simultaneous fill and decant? And how do you think that that will affect the sludge settling ability?
Well, we use the simultaneous fill and discharge, and there's also the third phase at the same time, because as I said, SBR, like any other processes, needs time, and saving time in SBR processes is important. And now because normal an SBR, we have the pure SBR, which finally is targeting to top and dot results, but that's another story. There must be the fill, react, settle, and discharge. And the normal settling time in an SBR can easily be 1 hour or 1.5 hours. And now we have settling time only half an hour. The settling starts at once, and it's going slower and lower and lower. And from underneath, there is coming the raw sewage, which is contacting the sludge and infiltrating through that, and the whole piston is moving slowly upwards. And at the same time as the treated crystal clear water is going up, the suspended solids are traveling downwards. And this is the way we gain the so-called safety margin there. And in the sludge blanket, there takes 3 phases at the same time, the fill, react, and discharge. Because the react is the anaerobic reactor, the anaerobic contact in between the incoming flow and especially the phosphorus and the sludge. So as I said, I'm an SBR man, and I have never said that I'm a active sludge man, but now it seems to be so that I'm an active sludge man. But this is a special sludge because the separation is the key. How the suspended solids separate from the surrounding bulk liquid, and that's the key. And when you have a safety margin of 2.5 meters in the piston, so there is no danger at all that the suspended solids would escape. But there is, of course, always the thin part or the fine part or the shared part of the sludge, which gives us the 2 to 3 to 4 milligrams per liter escaping suspended solids. And that is what we attack next. When we get that removed, 0.1 is standard.
Okay, because of the time constraint, actually we have a lot of interesting questions coming to you, but because of the time constraint, so if we have the time left at the end of the session, we can leave the question there. So now.
Yes, and for the audience, I can say that if you have a good questions, I receive them in written mode and try to answer everything. So
yes,
that no one is,
it will be very helpful. Yes, yeah, we will forward the questions to you. Yeah. Okay, so we move to the second speaker. Our second speaker is Professor Ana Soares from the Cranfield University. He is the professor of.
It means that I closed the presentation.
Yes, yeah. So, yeah. So Dr. Ana Soares is a professor of biotechnology engineering at Cranfield University. She specializes in environmental water protection and resource recovery. Her work focuses in municipal as well as the industrial wastewater management. Her scientific findings have resulted in leading-edge processes and technologies innovation. He is particularly successful in bridging the gap between the science and application, working in close collaboration with industrial and institutional stakeholders. Professor Soares is an AWA Fellow, active member of the various national and international committees, the editor-in-chief of the Water and Environment Journal, and associate editor for Journal Water Research. So I hand over to Professor Soares, please.
Okay, thank you very much, Young Chun, and everybody at the EBNet for the invitation to give this presentation. So, keeping within the topic, I'll be talking to you about options to remove nitrogen and phosphorus from municipal wastewater. And I'll be just touching very lightly on BNR processes, because I think Juhani did a really good job presenting the latest innovations on this area and how low concentrations of phosphorus can be obtained with biological processes. So before we start, I think looking at the options for nutrient removal, I think it's very important that we remind ourselves a little bit about the nutrient concentrations in a municipal wastewater treatment plant and where are these found in higher concentrations, so where we should be placing effort in relation to removing those nutrients. Removing the nutrients because they cause eutrophication and they can have very detrimental impacts if discharged and treated to the natural water bodies. And we have seen that regulation is becoming tighter and tighter in relation to phosphorus and nitrogen removal, both related with sensitive areas, but also also targeting industrial wastewater treatment plants. And so there's quite a lot of research and innovation going on in this area. And most efforts and technologies, they're based on mainstream treatment, where we have phosphorus concentrations between 5-12 milligrams per liter, nitrogen concentration between 13 and 60 milligrams per liter. Of course, this is dependent on the catchment, if there's trade effluents being discharged as well. And so we can have quite a lot of variation on this wastewater characterization. And so processes such as BNR might be applied. Chemical phosphorus removal, nitrification, denitrification are usually applied to treat this nutrient and achieve a high quality effluent. There's other stream that is quite important to consider, and this is the sludge, the watering liquors. So this will be originated from the watering of the sludges produced on site, primary sludge, secondary sludge, digested sludge. And this can have much higher concentrations of phosphorus and nitrogen. So up to 200 milligrams per liter of phosphorus. Usually we have around 60 to 70 milligrams per liter, but also high concentrations of ammonia, mainly ammonia. And this can reach values up to 2,500 milligrams per liter. And we see those very high concentrations, especially in sites with advanced anaerobic digestion, where there's things like advanced thermal hydrolysis, etc., that promote that complex solids within the sludge to be hydrolyzed to higher levels, and this really results in the solubilization of the nitrogen. And so, if the water liquors are recycled to the head of the works, which they usually are in many sites, then we see an increase of phosphorus and nitrogen up to 20–30%. And then this means that I have things like activated sludge processes or trickling filters, which dominate the UK landscape, will struggle to deal with those nutrients and still produce that effluent quality. And so, there's two different areas we can target for managing nutrients. So the mainstream and the side stream, both of them equally important, but we can manage them in different ways. And I just want to mention as well that, as Juhani was mentioning, sludge and the nutrients that accumulate in the sludge especially if we have a BNR process. There will be high concentration of phosphorus, as this is removed by capturing within the cell. Then, you know, a way of recapturing those nutrients is to recycle the sludge to land. There's a lot of initiatives as well looking into sludge ashes from thermal processes to recover those nutrients, especially phosphorus. And so there's a number of initiatives and processes. I think Johanni's presentation was mainly about BNR processes and removing the nutrients, but I want to focus here today is on the recovery of nutrients and why we should focus on recovering those nutrients. Well, phosphorus, you know, has been under debate for a long time. It's been called the disappearing nutrient. It's currently mined in quite specific countries such as Morocco and the Western Sahara. So there has sort of the biggest reserves of phosphorus, and there has been quite a lot of information out there about how much of phosphorus there is worldwide and how big are this mining reserves. And back in 2006, you know, there was some numbers being published saying that, you know, the phosphorus reserves were about to finish, that, you know, we had about 100 to 200 years left of phosphorus if we continue to mine at the same rate. And this has created a little bit of awareness, but also some countries that have quite a big production of phosphorus, such as United States and China, have started looking about their exportation of phosphorus in a different way. And this has created a debate about, can we capture phosphorus from the wastewater, and the best ways to do that, and then try to put that back into the market for example, chemical production, fertilizer production, etc. The other important nutrient that we've been talking here today is nitrogen. So the debate about nitrogen recovery, it's a little bit more contemporary. We just started looking into this a few years ago. And this is related not with the lack of abundance of nitrogen, as we see with phosphorus, but rather on the energy intensity that we go through to produce ammonia through the Haber-Bosch process, and also the amount of energy we spend to remove that ammonia in wastewater treatment plants. And I have some values here. You can see those numbers are absolutely huge, especially if we sum them up to produce ammonia and then put it back into the atmosphere. So to close the cycle, it becomes hugely expensive. And then there's the issue as well with the greenhouse gas emissions. So most biological processes, nitrification, denitrification, they will produce some sort of intermediate nitrous oxide emission. And quite a lot of efforts being placed nowadays to try to understand and quantify those nitrous oxide emissions. And there's a clear link between sort of the dissolved oxygen rate within activated sludge processes and the amount of nitrous oxide emissions, for example. And so there will be numbers in literature are highly variable, but you know, they are of concern, especially now with companies being worried with net zero targets and trying to reduce those greenhouse gas emissions. Nitrous oxide is a big concern. And so overall, resource recovery and nutrient recovery is very much aligned with world aspirations, looking at the circular economy loop and trying to close that. The UK government is investing vast amounts of funding on that net zero transition and trying to shift into a more greener economy. The same is lined up on the industrial strategy, grand challenges. And then, of course, at the center of this, we have things like the Sustainable Development Goals, where clean water and sanitation needs to be put into context with sustainable cities and communities, with industry, innovation, infrastructure, just to mention a few. So all of those things are sort of linked together and forcing us to look different ways into how we manage wastewater in general and nutrients. And so there's been a lot of work being done in the last decade, the last 2 decades, looking into both nitrogen and phosphorus removal and recovery. So within the biological processes, most of them are based on just removal. So we have nitrification, denitrification, deammonification with high technology readiness levels, so being applied at full scale, processes that we know very, very well and we can build, we can operate without many issues. In South Europe and other countries with a lot of sunlight, we start to see algae and algae develop related processes to remove and manage nitrogen. And currently, we see sort of a boom about ammonia stripping processes, mainly from sludge dewatering liquids or then digestates that have very high concentrations of ammonia. And within this ammonia stripping processes, some of them are not new processes. They are applied within other industries, chemical industry, for example, and we're sort of making that knowledge transfer to the water industry. And this is sort of us trying to recover that ammonia and then try to find a purpose to reuse it. And ammonia has also been gathering a lot of momentum, as it's been indicated to have a calorific value that is similar to diesel, so we can be combusted for energy generation. I think there's sort of a little bit of a debate if it can be burned in CHP engines directly or how best to adapt the existing infrastructure. Another reason that people are looking into ammonia and ammonia gas recovery is related with the fact that ammonia is an NH3, and so that H3 sort of is hydrogen, and so ammonia has been put forward as a hydrogen storage compound, also drawing quite a lot of attention. And there's two different things that I will mention to you in more detail, because at the core of some of the research that I'm doing. So ion exchange processes and the use of smart materials to capture ammonia from wastewater, and I will be presenting some of the data from a demonstration scale plant, and also some of the data from biological crystallization. So this has a lower TRL level, so we're still very much understanding the process at lab scale at the moment. And if we look now into phosphorus removal and recovery, there are a little bit more options for capturing phosphorus from wastewater, as we've been discussing. So BNR will accumulate phosphorus in the sludge, and this can be released once it's applied to the soil. There's algae as well. And then we have other processes that look into vivianite recovery, both related with chemical dosing for phosphorus removal, or then BNR processes. There's also the recovery of phosphorus from ashes and biochar. And I'll also be talking a little bit more in detail about this ion exchange process. And sort of, I think when we look into all these different technologies, and you can see, you know, I'm touching the surface about what they are and some of the options. There's much more described in literature. It's important that we don't forget how are these technologies going to work with everything else that is on site, and how we're going to integrate them into existing treatment plants. So in the UK, there's very few greenfield sites. So whatever we do, it has to be compatible with the older technologies that have been established for a long time. And so it's important that we think about things such as how we manage the byproducts. So for example, if I'm talking about the ion exchange process to recover nitrogen and phosphorus, this will lead into some chemical waste. So that needs to be managed. For example, within the ion exchange process, again, this works very well in a wastewater that has a low solids concentration. So what are the technologies that can make that ion exchange process work well as well? And ideally, you want to work and with local stakeholders and form the required partnerships. So when you recover those products, there's an end route for them. There's somebody that will be interested in taking them and making use of them. And this is not simple because there's regulatory frameworks to be considered as well. And so there's quite a lot of effort on this area of resource recovery. So in one of the projects that I'm involved in, sort of looking at that integration of resources and integration with stakeholders and regulation, is a European project called NextGen, where we have around 35 partners and 10 demonstration sites where we're looking to water recovery, nutrient recovery, and also some sort of energy recovery. And in this project, our role is to test and demonstrate a very specific type of wastewater treatment facility where we're looking into recovering energy from biogas production through a main treatment of carbon using an anaerobic reactor with a membrane. We also follow up with an ion exchange process to remove and recover the nutrients. And with this combination of processes, we can achieve a really high effluent quality that allow for water reuse. Because we're not dealing with the ammonia in a biological process and we capturing the carbon as biogas, we have very low greenhouse gas emissions, including the dreaded nitrous oxide. And of course, there will be savings as well from not aerating in the mainstream. And so we have quite an efficient process overall. So this process, as I said, is been deployed in Spurnal. So the anaerobic USB reactor, it's a 500 meter cube a day reactor that it's currently been commissioned, and we hope to achieve some data very soon. The data that I have, that I'm showing you here now, is related with some of the pilot scales that we have run at Cranfield. And here we have the effluent quality that can be achieved from the USB membrane reactor. So the membrane allows for no solids in the effluent, and we can achieve in average BOD concentrations of 5 milligrams per liter. So an extremely good effluent quality, like I said, suitable for reuse. And we also got to produce some electricity from the biogas, but we're also going to produce a massive amount of heat. So we're looking into ways of reutilizing that heat in a meaningful way. The beauty of having a USB coupled with a membrane is that we can promote hydrolysis, so we can retain all the solids inside the anaerobic reactor for long periods of time, and we can achieve methane yields that are very comparable with traditional anaerobic digestion processes. So what this USB membrane reactor doesn't do is touch the nutrients. If anything, we'll see an increase of both ammonia and phosphorus, once again, due to that solids hydrolysis. And the effluent will contain the same amount of nutrients as you will have in your influent, plus minus 20%. And so we would need to remove those nutrients. And we, as I was mentioning, we've been studying ion exchange, different types of media, and this has led into this demonstration scale plant where we fed 10 meter cubes a day of wastewater. The treatment plant, as you see here, is very small because we keep contact times very short. So for phosphorus removal, we use a hybrid ion exchange resin, which is commercially available. And this material, this smart absorbent, is coated with phosphorus it's coated with iron nanoparticles that will capture the phosphorus from the wastewater, and this bond can be reversed just by an increase in pH. So this allows us to then recover the phosphorus from the regenerant. And for ammonia removal, we used a polymer called zeolite N, and this works as an ion exchange material, and we can exchange ammonia with potassium and sodium. So we have kept this plant in operation for over 2 years here at the Cranfield Wastewater Treatment Plant. So treating wastewater winter, summer, over a number of cycles. And our aim here was to understand how stable the process was. We had done some pilot trials before, but we were never been able to run it for more than 6 months, 3 months, and so on. So there was a big question mark, sort of what happens to the ion exchange smart material, to that polymer resin after extended period of time. Do we need to change it frequently? Can we regenerate it over extended periods of time? Can we recover the phosphorus? And so this graph here just shows you the different cycles of absorption and regeneration. So this is when the phosphorus concentration goes down, and then we start the cycle again, absorption, regeneration. And we could safely remove phosphorus from initial concentrations of 6 milligrams per liter to concentrations below 0.3 within an average of 430 bed volumes. So that will tell you how many bed volumes can you operate the bed before you need to regenerate. And we could reuse the regenerant. So the green line that you see here is the regenerant, which was sodium hydroxide at 2%, being reused a number of times. And what happens if we try to reuse this more than 7 or 8 times is that, you know, it becomes quite saturated with phosphorus, reaching up to nearly 800 milligrams per liter of phosphate, and it can no longer be used as a efficient regenerant. And so what do we do then is that we remove the phosphorus from the regenerant. So we just add a solution of calcium hydroxide. The calcium would precipitate with the phosphorus in a quite instant reaction, and we can precipitate it and filter it and dry it in order to produce calcium phosphate. So during the operation of this plant at Cranfield, we produced many phosphate that we trials of investigating its fertilizer value. One of the things we observed, it was that over time, we always saw a little bit of COD removal after the phosphorus removal column, about 20 to 30%. And so over time, the resin became coated with this carbon that we have found to be some sort of humic acid, so recalcitrant carbon. But then we can clean the resin by regenerating with sodium chloride. We estimate that probably this needs to be done every 6 or 7 months, depending on the quality of your wastewater, to keep a healthy resin, so you can use it for a very long time. So we sort of looking into the product quality as well, and we saw that they had very, so the calcium phosphate had very low concentrations of impurities, including organic. So we tried a few, we tested quite a few of them, including priority substances, and it had very little concentration of heavy metals, much lower than, for example, the phosphates that we mine, and you know, opening sort of a range of routes for its application, and looking at different markets as well. So you know, we have done quite a comprehensive study here. I just sort of there's not much time to go over all the details, but happy to answer any specific questions that you might have at the end of the presentation. We also consider, you know, to be of high relevance to have processes and technologies that can be integrated, but they have some sort of benefit for the environment. So that will be seen clearly when we sort of manage and recover the nutrients a little bit better. But it's also important that it make economic sense and it will have some sort of economic benefit. So wastewater treatment plants are not there to make money. They're not there to be self-sustained. There will always be required some investment, even if we sell all the imaginable products from wastewater treatment plant, they're still going to have an OPEX that needs to be covered somehow. So one way of measuring the benefit of a certain technology or a treatment or a combination of technologies, it would be sort of to compare it with existing ones. And so here what we did was to compare the capital costs and operational costs of a traditional BNR plant with a plant where we have the ion exchange processes and one where we have the anaerobic membrane reactor and the ion exchange processes. This is without considering any potential economic benefits from selling products. And we could see sort of the whole life costs of the anaerobic membrane ion exchange process are higher than compared with the traditional technologies. And of course, you know, this requires for people to have a long-term vision a little bit. You know, those economic benefits are not going to be turned around in 3 years or 5 years. So there's going to be a little bit longer to realize all those benefits. But you know, if we want to recover products from wastewater, then you know, maybe this is some of the steps that we need to do and think about sort of on the longer term and what the benefits might be. Another sort of project of mine that I find really interesting looks into biomineralization, and so this is related with the ability of microorganisms and bacteria to produce minerals from their biological reactions. And biomineralization has been quite well studied and documented in biomedical sciences. For example, kidney stones are produced by infectious bacteria that lodge in people's urethra and around the kidneys. And so there's quite a lot of documentation about those. But we know that this biomineral formation ability is quite widespread in the environment and nature. And there's been over 60 different minerals being documented, including struvite, calcium phosphate, just to name a few. But we don't know much about this bacteria, and especially how we can apply them to wastewater treatment plant. And so I have spent quite a bit of time trying to understand sort of what are this, how is this biominerals are produced and what are the mechanisms behind this. And there's mainly two different ways where bacteria produce biominerals. One is called biological controlled mineralization, and the other one is called biological induced mineralization. And in both ways, sort of the bacteria find a way within their mechanism to increase supersaturation of the elements. They're going to form crystals within sort of their surrounding environment, or then intercellularly forming nucleation points. And once this nucleation point are formed, then crystal aggregation and crystal growth can happen at quite high speed. In biological controlled mineralization, we see beautiful crystals with all of them very homogeneous in size and shape, while in biological induced mineralization, the process takes outside the cell, and then this leads into the formation of crystals that are a little bit more heterogeneous in size and shape, etc. But yeah, both of them really quite interesting. And so we've been studying different bacteria that produce biominerals, and we've been incubating them in sludge dewatering liquors. So with concentrations up to 30 milligrams per liter of phosphate. The specific sample we studied had an ammonia concentration of 300, and you can see the rest of the characterization here. And after sort of 4 days of incubation, we can see this beautiful crystals being formed, and bacteria, for example, such as Brevibacterium anticum, could remove up to 79% of the phosphorus. We have also incubated this bacteria in the mainstream, so in the just settled wastewater, and we could also reach phosphorus removals up to 95%, 99%, so reaching effluent qualities of 0.5 milligrams per liter of phosphate. So a very interesting process for working mainstream and side stream. These crystals, they can reach up to 500 micrometers, and so we can quite easily remove them through a simple filtration process. So nothing too complicated in terms of separation. We have been assessing also the fertilizer value of this recovered struvite. So we've been doing this in the small scale petri dishes, as we've seen here, and in the case of the biostruvite, we see that the phosphorus becomes readily available in the soil, and looking at the length of the roots and the stem, this case it was in mustard seed, we also see that the biological struvite performs very similarly to other synthetic fertilizers. We also looked into the composition, tried to look for other pollutants, and once again, sort of we obtained a fairly clean product with up to 12% grams per kilogram of phosphorus. So very similar to other recovered struvite products. At the moment, sort of, this is still a low TRL technology. So all the studies we have been completed with pure cultures. So we've been trying to understand how we can take this process further. And one of the challenges is working in mixed culture settings. And we have tried to add some cultures of Brevibacterium anticum, for example, to the watering liquors. And of course, it gets that culture gets completely obliterated by the competing microorganisms. And so to go around this, we're working with a company called MicroV Technologies, where they produce a catalyst where we can sort of encapsulate our struvite producing bacteria. And this way, sort of, we're trying to upscale the technology and work with the mixed cultures, both in wastewater, and currently I'm also looking into urine treatment in decentralized systems. And the centralized systems are gaining also quite a bit of a relevance because we see that as the public is gaining a little bit more of understanding of their carbon footprint, and technologies are being developed for applications sort of a more local level, looking at sort of local supply chains, etc. So the centralized systems are gaining quite a lot of attention, and where we can produce water for reuse within a block of flats or within a household, through sort of usually there's going to be a gray water to a black water separation from the black water treatment. Then through anaerobic processes we can produce heat and electricity to put back into the household. And so the solids might be reused for the local garden or community centers. So there's quite a lot of potential in this way of seeing wastewater treatment. And so we've been also using this concept of biomineralization to understand if we can recover nutrients from urine, and actually we've been doing that quite successfully. This is just some very preliminary data, but we can see here that when we incubate Brevibacterium in urine, we can produce a large amount of precipitates, and we have identified those precipitates as struvite as well. And so this could be another potential way to try to recover nutrients in the centralized systems. I think we cannot talk about resource recovery without thinking about the pandemic and COVID-19 and how is resource recovery, especially of the things that I was talking about, sort of salt and solid, but even sludge. And how is this going to affect us in the future? And I think, there's not a lot of regulation currently on, or well, just very prohibitive regulation on resource recovery from wastewater treatment plants. And so, there's a need to understand that a little bit more in depth, and for us to provide, information on the quality of those products with quite a lot of data and confidence behind it as well. But I think sort of we need to think about this resource recovery as a manufacturing process, you know, where we have procedures, we have quality control, there's customer relations as well. And there's quite a few good case studies, for example, taking place in the Netherlands, where resource recovery from wastewater treatment plants has been made an absolute success. But those things are quite imperative that they take place. And I think we need to unify ourselves as well, especially bringing sort of a single message and battling misinformation. You know, I have seen all sort of news about sludge recycling to land and COVID being there or not, and it's just sort of just scaring people. So we need to think about how to convey those messages and you know, help drive resource recovery. About future perspectives, I think a lot of the drivers that we see currently and where we are, probably the next generation of technologies, I think will be hugely influenced by this net zero targets, and combined with sort of this more rigorous regulations and the need for water reuse as well. So in the future, I think we will see more technologies that actually recover gases. That could be, you know, ammonia gas, biogas, maybe not for burning and producing energy, but maybe to produce chemicals and other interesting compounds, methanol. We can combine nitrogen and the biogas to produce protein. So this is something that we currently looking with some colleagues in Europe. And so the possibilities are endless. It's just sort of a lot of the technologies we're currently working on, they're still sort of reaching that sort of technology development, just about to go into technology demonstration. So I think the next decade will be critical to reach those higher TRL levels where we see implementation of these technologies at full scale. And I'll be very much looking forward to that. And I'll thank you so much for your attention. And I'll be happy to answer some of your questions as well. Thank you.
Thank you, Anna, for your presentation. I think there's a questions. Although our time is 1:30, I think it's better to take 1 or 2 questions from the audience first. So there's one question about the decentralized wastewater treatment. Is this the proposal, for example, for the UK, or if so, what time scale to replace existing infrastructure, or only for the new building or elsewhere?
I think this would be mainly for new buildings. It will be of higher relevance. It's just sort of existing buildings, you know, and changing existing infrastructure, meaning piping, heating systems, will be too complex and too expensive as well. And so I think this will be more relevant for new builds, and especially in the UK. You know, in other countries where there's no infrastructure, might be that, you know, they take on a different approach as well.
Okay, so I think another question is about for both speakers, biological removal or chemical absorption of the phosphorus, which works best under what circumstance? For example, for farm use, or what else? So probably Johanna first. So for biological removal of the P, because the P is accumulated in sludge, can we directly use that P-rich sludge for farm?
Well, in my home country and in total Scandinavia, it has been researched very deeply and looked at it after the phosphorus. The first phase was, of course, because the chemical dosing was nominated, so it was the sludge composting. But nowadays we have several processes here under discovery and under research, which I do not know exactly, but one of my old friends is working with that, and I have seen the test plan. And the thought is here that it will be a short distance deliveries. So it would be local, small plants and local. And my thinking now, when I've seen the NUTREM and all those things and the phosphorus removal, the scale difference is huge. In big plants, the result or the solution has to be simple and robust and functioning and economical. There is so much dreaming at the small end what can be done, because I understand that the whole world is moving towards green. It's going greener, but we have to remain our realities.
Okay, thanks. So Anna, for the chemically recovered peat, I saw that you monitor heavy metals as well. Did you monitor the quality of the heavy metals and compared with digestate, which currently applied to the land in the UK? Did you compare the quality between for them in terms of the heavy metals?
Yeah, so yeah, it's data that we have, I just haven't presented here. So the calcium phosphate that we recover, it has a very high purity. So if you think the wastewater will go through preliminary primary treatment and then through the USB membrane reactor, and that membrane will help to remove a lot of the pollutant. And then the phosphorus is selectively captured within the ion exchange, and then we move that into the regenerant, and then we precipitate the phosphorus from the regenerant. So it's an extremely pure chemical. You know, there's quite a lot of processes that are quite selective for phosphorus recovery, while, you know, anaerobic digestion, basically all the sludge that goes to site goes into the anaerobic digester. So you will find much higher concentrations of heavy metals there.
Okay, I think there's one question about the specific technical details. I don't fully understand. I just ask the question based on my understanding. So is it ask if the nano, you mentioned that you use the iron nanoparticles coated iron resin to exchange with the phosphate. What is the function of the iron nanoparticles? How that can be used to remove phosphate?
Yeah, so that resin is coated with iron nanoparticles, and it's the iron that forms a complex with the phosphorus that allows for the selective removal of phosphorus from the wastewater. So it forms a weak bind, and then, you know, we can then unbind the iron from the phosphorus just from short contact time with the sodium hydroxide, so pH 12 solution. So we wash the resin, and that binding, it's like I said, is weak binding. So the phosphorus becomes soluble again, but on the sodium hydroxide solution. So, and then we can recover it from there.
Okay, thank you very much. Because of the time constraint, it is impossible for me to ask every question from the audience. So probably EBNet will write down those questions and pass to the speakers. I don't know, Angie, is it possible?
Yeah, we're happy. I've got the questions down, and we can pass them to the speakers. Yeah, not a problem.
Okay, okay. I think that's I pass to you, so you probably give the, yeah, what do you have to say? Because okay, this is the end of the session already, yeah.
Yeah, well, apologies for running slightly over time, but thank you all ever so much for coming today. Recordings will be available upon speaker agreement. We'll make a list of the questions and fire them off, and we'll probably put them on the website, or when we let you know, we'll let you know where the answers to the questions have ended up. Louise and I'd like to thank you, Young Chang, for chairing the session. Extra special thanks to Juhani and to Anna for your fascinating and really relevant presentations. We will be sending an online feedback form, so we'd be very grateful if you all can fill it in. It does help us to frame the activities for the network, which is, after all, your network. We hope you're able to join us for a future event, and we'd love to see you soon, either virtually or in real life. Thank you ever so much for coming, everybody. Cheers, and see you soon.
Okay.
Thank you.
Thank you. Bye.
Bye, Juhani. Bye.